Welcome. This video will present the topic of asymmetric load sharing. The applications will be presented, along with an example of a solution for a wet stacking effect. Asymmetric load sharing is a function in which the controller intentionally distributes active power unevenly between sources operating in parallel, even though the total power exactly covers the load demand. Let me present a few examples of applications. It can be used when combining different types of sources, such as diesel and gas. These machines often have different dynamics and operating limits, so we can run one as a stable base load unit while the other handles transients and fast load changes. Another application could be combining units with different rated power. Instead of forcing equal kilowatts or equal percentage sharing, we assign load more appropriately so the smaller unit isn't pushed into its limits, and the larger unit doesn't run inefficiently. It can be helpful in optimizing fuel consumption. If one unit has a better fuel curve in a certain range, we can preferentially load it to reduce overall fuel use while still meeting the total demand. Another important use case is inhibiting wet stacking, especially in diesel units that operate at low load. So let's move on to the next slide and take a closer look at what wet stacking actually is and why asymmetric load sharing can help prevent it. Wet stacking occurs when an engine fails to burn all of its fuel. Instead of being burned, the unburned residue passes to the exhaust side of the turbocharger and ultimately to the exhaust system itself. The main reason for this is the engine running at low power. When the engine runs below its optimal temperature or with an incorrect air-fuel ratio, combustion is incomplete. You can often spot this visually. Look for black ooze around the turbo or exhaust pipe connections, or black smoke coming from the exhaust while the engine is under constant load. If left unchecked, the consequences are significant. You will see an immediate loss of engine performance. Over the long term, this leads to premature engine wear and can cause permanent damage to critical engine components. To solve this problem, it is recommended to periodically run the engines at increased load. By periodically increasing the engine load, we raise the operating temperature, burning off excess residue, and maintaining optimal operating conditions. However, to do this safely, we need to meet a few key requirements. First, there must be sufficient load available on the bus. We must ensure that other engines do not go into reverse power when we ramp up the target engine. Second, we must maintain system stability across the remaining gensets. This is where the flexibility of the Woodward easygen controller comes in. To automate this process, we utilize the free derating function, but configured in an uprating mode. To understand how to configure the easygen controller, I will use an example illustrating the situation in question. There are two generators G1 and G2 running in isolated operation, each has rated equals 200 kilowatts. Most of the time, each generator operates in symmetrical load sharing with a rated power of 25%, which means that the two generators together have power of 100 kilowatts. This situation is illustrated in the graphic on the left. To control wet stacking, every engine shall be uprated at least to 30% for 30 minutes. This results in an asymmetrical load sharing, as shown in the graphic on the right. Generator 1 should do this on the first day of each month, and Generator 2 on the second day of each month. We will now go through the parameters that need to be set in the controller. First, go to the derating power section and set the direct derating parameter to on. This will cause the analog manager derating source, visible on the right, to directly specify the change in rated power. If we set the value C1 to more than 100%, it will be an uprating; if less, it will be a derating. Then set the logic manager as shown in the attached figure. When the free derating flag is set to true, uprating shall become active. Then go to the analog manager mentioned earlier and configure the parameters there. Change the mode to constant and enter the value C1, which determines the reduction or increase in power depending on the value. For more information on calculating this value, see the application note linked at the end of the video. Next, set the timer so that the process starts automatically on the first day of the month for Generator 1 and on the second day of the month for Generator 2. When the timer is active, this is indicated by LED 10943 active day. The next step is to set the uprating duration. First, select one shot type. Next, select variable LM, flag 1, which is a start condition, activating the one-shot mode for 30 minutes, which is 1800 seconds. The one-shot can be stopped before the time expires if the flexible limit becomes active, which is stop condition. This is to avoid overload or unnecessary uprating. The binary output 91.01 of this analog manager is passed to the logic's manger-free derating to start uprating. The final step is to set the start and stop conditions. The internal flag 1 becomes true if the selected day is true and the power is not more than 45%, defined with flexible limit 1. The output is passed to analog manager internal value 1 to trigger the one shot and start the uprating. To avoid overloading the generator, it is necessary to set the maximum limit to which its power can be uprated. This requires configuring the limit in the flexible limits and in its corresponding analog manager. In our case, the power limit is 45%, and the monitored value is the total active power of the generator. If this limit is exceeded, the uprating will not start, or it will be stopped if already in progress. For additional information about Woodward devices, including manuals, software, compliance certificates, and other documentation, please visit our documentation server. This resource provides everything you need to support the configuration, operation, and maintenance of your Woodward products. Additionally, I encourage you to read the application note 37663, which shows the necessary calculations for inhibit wet stacking functionality. Thank you for watching.